Space is silent. There's no air to carry sound, no wind to deliver whispers. And yet, for over 6 decades, we've been speaking across it, not with voices, but with waves. From our earliest satellites to interstellar probes billions of kilometers away, we've found a way to keep the conversation alive. A spacecraft may be distant, alone, and tiny against the black canvas of the universe, but it's never truly silent. It's always talking, sending home its findings, its health, its position, via invisible pulses of energy. For decades, this language has been carried by radio waves, a form of electromagnetic communication reliable enough to navigate the solar system. These waves are patient, durable, unshaken by cosmic weather or planetary rotation. They've been the backbone of mission after mission, from Sputnik to Voyager, from Apollo to Artemis. But as we prepare to push farther than ever, to Mars, to the moons of Jupiter, to deep space telescopes, our needs are evolving. We want more data. We want it faster. We want live video, real-time diagnostics, and the ability to send and receive massive streams of information at the edge of the solar system. And for that, we need a revolution, one made of light. This is the story of a technological duel, a comparison of two titans, radio and laser communication. The old reliable versus the focused beam of the future. How do we talk to our spacecraft? And how will we do it tomorrow? A spacecraft is only as valuable as its ability to communicate. No matter how advanced its instruments, no matter how well built its systems, if it can't tell us what it sees, it might as well be silent space debris. Communication is the thread that ties every mission to Earth. It lets us send commands, adjust trajectories, download scientific data, and monitor spacecraft health. Without it, a billion-dollar probe becomes a floating question mark in the void. But sending messages across space is no small feat. Even a nearby planet like Mars can be tens of millions of kilometers away. A signal from Earth takes between 5 and 20 minutes to arrive, depending on orbital alignment. That delay means every instruction must be deliberate, calculated, and reliable. Now imagine communicating with a probe at Neptune, or even farther, like Voyager 1, over 24 billion kilometers away. The signal that leaves Earth takes over 22 hours to reach it, and the return trip takes just as long. This delay is bad enough. But now consider bandwidth, the amount of data that can be sent. Most deep space missions use data rates that seem shockingly small by today's standards. Sometimes only a few kilobits per second, slower than a 1990s dial-up modem. To meet the demands of modern science, we must evolve. We need better speeds, more capacity, and greater precision. We need to upgrade the way we speak to the stars. Radio communication has been the workhorse of space exploration since its inception, and for good reason. Radio waves are incredibly versatile. Their long wavelengths allow them to diffract around objects, penetrate through planetary atmospheres, and resist interference from cosmic dust and solar radiation. They can be broadcast in broad beams, meaning a spacecraft doesn't need pinpoint alignment to communicate effectively. This has been especially useful for early missions, where precision pointing was difficult or impossible. And perhaps most importantly, we've built decades of infrastructure around radio technology. NASA's Deep Space Network, DSN, is a marvel of human engineering, with enormous 70-meter dishes spread across the globe in California, Spain, and Australia. Together, they provide uninterrupted coverage of nearly every spacecraft beyond Earth orbit. Through this network, we've received the haunting photos of Titan's methane lakes, the seismic data from Mars quakes, the first close-up images of Pluto, all from the slow, patient whisper of radio waves. But as capable as it is, radio is hitting its limits. It was never designed to handle gigabytes of data streaming in real time. It wasn't built to accommodate hundreds of simultaneous missions, all asking for more bandwidth. The network is strained, and the solution may lie in something much faster and far more focused. Laser communication, or optical communication, isn't science fiction anymore. It uses near-infrared light to transmit data, tightly bundled into an ultra-narrow beam. Instead of broadcasting broadly like radio, laser systems focus like a sniper, shooting a precise stream of photons across vast distances. The difference is dramatic. A typical deep space radio system might manage 20 to 100 kilobits per second. A laser system? It can push hundreds of megabits per second or more, a thousand-fold improvement. Laser comms also enable smaller, lighter hardware. Optical terminals weigh less than large dish antennas, a major advantage for compact satellites and future crewed missions. And because the beams are narrow, there's less interference from background radiation or other spacecraft. Multiple missions could transmit simultaneously, a must-have for a future filled with rovers, orbiters, and human habitats. In 2023, NASA's DSOC, Deep Space Optical Communications, experiment aboard the Psyche mission achieved something unprecedented, successfully sending laser signals across interplanetary space. The results? Crystal clear, high-bandwidth communication from a spacecraft heading toward the asteroid belt. The future has begun, but it's not without its obstacles. Lasers may be fast, but they demand perfection. Unlike radio waves, which spread and tolerate small errors in pointing, lasers are extremely narrow. To maintain a stable link, both the spacecraft and Earth-based receiver must be aligned to within a fraction of a degree across millions of kilometers. That's like trying to shine a laser pointer from Earth and hit a moving coin on the moon, while both you and the coin are drifting in different directions. And there's the problem of Earth's atmosphere. Clouds, turbulence, and even daylight can scatter or block laser signals. Ground stations need to be placed in high-altitude, dry locations, like mountaintops or deserts, to minimize distortion. Then there's power consumption. High-speed lasers use more energy than radio transmitters, posing a challenge for deep space probes relying on solar panels or small nuclear batteries. Finally, laser communication requires new infrastructure. Optical ground stations, adaptive optics, orbital relays, all must be built and tested before lasers can become standard. Laser is not here to replace radio, at least not yet. It's here to complement it, to pick up the slack, to supercharge the missions that need speed. Together, radio and laser form the future of space communication. Soon, humans will walk on the moon again, and shortly after, Mars. These missions won't just collect rocks. They'll require real-time coordination, remote support, and constant communication with Earth. Astronauts will wear smart suits. Rovers will scout ahead autonomously. Base stations will manage life support, solar power, and navigation. All of this generates data, tons of it. And when we have crews living months at a time on Mars, they won't just want mission updates. They'll want connection to their families, to mission control, maybe even to the internet. Laser communication offers the bandwidth to make that dream real. Imagine streaming high-definition video from a Martian greenhouse, downloading software patches in minutes, hosting a video call across planets, delayed by distance, but crystal clear. With laser comms, the divide between Earth and Mars becomes not a void, but a bridge of light.